Hello, everybody, and welcome back. We are here for week 2 of our new series, Database Deep Dive with Nick and Randall. We have an amazing guest here this week, Rick Houlihan. We're going to be talking a little bit about DynamoDB, NoSQL databases, and we're going to dive deep and figure out all of the nuts and bolts around how it works and when to use them. But first, let's go down the aisle. Randall, you want to introduce yourself quickly?
Everybody, my name is Randall Hunt. I'm a software engineer and technical evangelist at AWS, and I worked a lot with Rick in the past. We actually both used to work at MongoDB back in the day. And Rick, tell us a little bit about your role.
Sure. My name is Rick Houlihan. I'm a principal technologist for NoSQL Technologies, primarily focused on DynamoDB, but I work across stacks. I talk a lot about NoSQL data modeling, and that's really what we're here to talk about today.
Now, Rick, I'm here to remind you today that you and I both spent some time in New York, and we speak a little quickly. So
You're not the only ones. I'm from New York, too, so we're all on the same page here.
We understand that, or at least I've received the feedback in the past that perhaps I should speak more slowly. So we're going to try and keep it at a gentle rate today. And then once we get into the deep dive, you and I, we can just go
That's right.
New York speed.
Exactly.
So can you tell us, we talked in our previous episodes about how to choose the right database for the right job. We talked about all the different categories of databases that exist. I mean, DB Engines in 2019 is tracking 329 different database engines. And as a developer, as an architect, as an engineer, it is frustrating and difficult to ascertain how I'm supposed to choose what the right database is and how I'm supposed to get it right on that first iteration.
Sure.
But one of those kind of stores, one of those categories is document stores or key value stores or key blob stores. I'm curious, where does DynamoDB fall in this, and what is DynamoDB?
Yeah, absolutely. That's a really good question. I get that a lot when I talk to customers. Everyone wants to know, when should I use a document store? When should I use the wide column store? Well, what's a key value store? And the reality is it's all NoSQL. And I think hopefully when we get through some of the data modeling discussion we have today, people start to realize that the same patterns apply, and the document structure versus the wide column structure is really rather irrelevant. And I think that when people start to get into understanding what NoSQL is about, all of these technologies generally work the same. I always like to say you can treat MongoDB, and I know this is getting ahead of myself maybe, but I treat MongoDB as a partition key only Dynamo table. Because that's what it is, right? We index the items in a MongoDB collection similar to the way we would index the items on a partition key only MongoDB table to produce the results we need.
We want those B trees.
We want those B trees, that's right.
Okay, so yeah, without going too deep right away, let's talk a little bit more about NoSQL, right?
Sure.
So like, how did it come about? How did we arrive at requiring it as another optimized solution to a set of problems that we face as developers?
Sure. So actually, that's a really good kind of talking point here. We can get into the charts that I brought, where we can talk a little bit about some of the things that you just discussed, right? Well, how did it come about? Why do we want this? Why am I concerned with this as a developer? So this presentation is really, when we'll break it up and talk a little bit to this subject, feel free. But generally speaking, it's about why and when to use NoSQL and how to model your applications for NoSQL. So we'll talk a little bit about overview of DynamoDB, of course, but we're really going to get into the meat of things, which is the modeling, the NoSQL data modeling, right? That's what
And maybe we can start at the beginning and kind of think, hey, why do we build databases in the
why
first
do we
place?
do this at all? Exactly.
Why are there 300 of them today, right? There's got to be a reason.
There's got to be a reason. So let's talk about that. So let's talk in the timeline of database technology. There's been an evolution of what I call peaks and valleys in data pressure, right? A series of peaks and valleys in data pressure. And the data pressure is about the ability of the system to process the amount of data we're asking to process in a reasonable time or a reasonable cost. When one of those dimensions is broken, that's a technology trigger, and we're going to invent things. And we've invented many things over the years. So if you look at the first database, is the one between our ears. It's a really good database. It's highly available, right? When my eyes are open, it's always on.
Hopefully, at least.
Generally speaking.
What about durability?
You got it, right? Durability questionable. Fault tolerance is about 0. It's a single user system, right? And so we actually had to invent other things. So we invented a system of ledger accounting, which really was the first database, right? We wrote things down. And ledger accounting drove public and private sector applications for millennia. Until
Mesopotamian style.
Yes, exactly. Until 1880 U.S. Census came along, and a guy named Herman Hollerith was tasked with processing all of that data. The U.S. Census runs on a 10-year interval, and it took him 8 years to process the data from the 1880 census. So he kind of figured in 1890 that job's going to be a little bigger than the 10 years is going to allow him to. And he invented a new technology. The machine-readable punch card and the punch card sorting machine era of modern data processing was born. So rapidly, we started to drive through many technical innovations: paper tape, magnetic tape, distributed block storage, random access file systems. And around 1975, 1980, we landed on a really neat technology that seemed to solve all our problems. It was the relational database. And we had the answer to everything, right? But it's important to understand the reason that the relational database was invented was to decrease the pressure on storage. Because storage was the #1 expense in the data center in 1970. As a matter of fact, a 4 megabyte hard drive cost somewhere around $250,000 in 1974.
It was also the size of this table.
It was also the size of this table.
So not only does it cost a lot, you have to buy a bigger building every time you want to expand your storage, right?
And so, and now obviously we weren't storing a lot of data on magnetic disk then, but just to give you the example of the cost of storage, and the relational database did a very good job by using a normalized data model, which deduplicated the data on disk. It gave us an ad hoc query engine to be able to reproduce the views of the data that we wanted to see in our applications. This was really good in 1975, 1980 because storage was expensive. But when we fast forward 30 or 40 years, now all of a sudden storage is cheap. And this is why we're looking at NoSQL databases. NoSQL databases use a denormalized data model, which is highly tuned to the access pattern in order to specifically support a given workload. And we'll talk a little bit about how we model data that way. But what we're doing is we're reducing the pressure on the CPU. And the way we're doing this is by increasing the pressure on storage. But that's okay because storage today is pennies per gigabytes. We pay dollars for CPU seconds. So we want to optimize the most expensive resource in the data center, and that's what we're doing with NoSQL.
So it's an optimization problem in the end.
That's
We're
really
still storing the same information. Sometimes we're duplicating it, or we're paying a storage cost in order to get a CPU benefit.
Right, absolutely, and that's the key, right? We don't want to use technologies that are maximizing the least expensive resource in the data center. We want to maximize the most expensive resource in the data, or optimize the most expensive resource in the data center.
So where do we stand in the adoption of,
So that's so right now, and this is really what's true with every technology. When we start to look at bringing new technologies in for developers, we start to try and use these technologies the same way we use the old technologies because that's what we know. And this is why I see most commonly in NoSQL now working with teams. And I've worked with thousands of teams, literally thousands of teams at this point, including a large chunk of Amazon's internal retail services as we migrated from Oracle to DynamoDB. And I've seen it again and again. We take the relational models that we're familiar with, the normalized data models, and we try to translate those to NoSQL, and we have a miserable experience. And so that's what this chart is about. If you look at the bottom of this, it's the adoption curve. In the beginning, we have a technology trigger that's forcing some innovation. The innovator is going to come up with some sort of solution. Other people with similar problems are going to try and use those solutions, and they're going to fail. They're going to fail repeatedly, and they're going to think that this technology doesn't work. But the reality is because they didn't really learn how to use the new technology before they deployed it, and that's because the skill sets are rare. And so if you look at the adoption curve for NoSQL today, we're in that early adopter chunk right there still.
you still think we're in the early adopter?
I really do.
Wow.
Interesting.
Yeah, I think that because of the nature of the skills, or the commoditization of the skill sets has not yet occurred. I talk to way too many teams today who are still trying to do things the old way. When I start talking to more and more teams, and I feel I'm talking to more teams that know how to do it than don't, then I'll feel like we're in that early majority.
So do you think that we are, where does something like SQL stand? It's
out on the right in there on the laggard side. If you don't know what a join is, I can't help you. You've been a K for 30 or 40 years.
So what is kind of, when do you think SQL and relational storage reached that point? How long did it take?
It's funny because I remember back in the day, and I might be aging myself out now, but I used to interview developers and ask them what's an inner join. What does write me an SQL query to produce a view that combines these three tables.
How does a Venn diagram work?
How does a Venn diagram work? Right. But these were the questions we used to ask developers, and developers used to do crazy things with relational databases, right? Mm-hmm. We used to see these big, giant, flat tables with 1 million columns, and most of the rows had null values on 90% of the columns, right? This was the kind of things developers were doing with relational databases, right? So, we would never do this today, but they eventually learned the skills, right? It's hard to say when, as far as timing, this is going to occur, but I think what we'll know is when we start meeting with customers and they already have an idea of what they're doing and they're doing their job relatively well, with designing NoSQL data
Personally,
models.
I would have thought we were an early majority already, because the developers I talk to, they're pretty familiar with NoSQL at this point.
Oh, I think I talked to a lot of developers who think they're familiar with NoSQL.
I think one of the big issues here is you sort of have like two separate problems that NoSQL you need to understand to assess whether NoSQL is right for you.
Right.
The first is sort of like, what is your data model? And that can be a little bit more objective, right?
Sure.
You can make a checklist. You can say, how sparse is my data set? How many different features do I have across the objects in it? But then ultimately, something that the engineer has to figure out on their own is, what are my access patterns?
Mm-hmm.
What is the read pattern? What is the write pattern? And those aren't really like binary answers, right?
That's
It's
right.
not like, hey, I read a lot, or oh, I write a lot. It's like, well,
Absolutely.
what is the distribution of those reads and writes? And that is a really tough problem to write generalizable content around,
That's
because
right.
you have to run your own experiments.
And that's the crux of NoSQL. It's not generalized, right?
Mm-hmm.
You look at relational databases and normalized data models. There's a lowest common denominator. It's the third normal form, and we can always describe your data set in that kind of third normal form, normalized model. But when you get into NoSQL, it's so specific to the access patterns. You made some really good points. When do I optimize for the read versus the write? Okay, that could be a really big deal. If the read velocity is high and the write velocity and the update velocity is low, then I'll optimize for the read. But if the write velocity is really high and the read velocity is low, it's the other way around.
Yep.
And those models are totally different when you get down to actually storing the data on the table and how I'm going to put it in there.
Yeah. So that was a lot, and I know we'll get more into use cases and examples, right?
Sure.
Because that's just a lot of the theory around of NoSQL. But basically, from a broad perspective, can you tell us a little bit more about like the apples to apples comparison?
Sure,
of
when
SQL
to
and
use
NoSQL?
one, when to use the other, sure. So we've got a good chart here for that. When you talk about NoSQL, it's really not for everything. NoSQL works really well when I have a well-defined access pattern. So what does that mean? It really means if I'm looking at transactional applications, OLTP, online transaction processing, where every time the data gets processed, the same things are happening. I think Amazon shopping cart, right? When I add things to my cart and I buy my order, the same process occurs on that data, no matter how many times the orders are made. It's not that we process orders differently every time the button gets clicked. This is a really good application for NoSQL, and it's actually really good for us, because NoSQL or OLTP applications make up about 90% of the common business processes, right, that we are coding for today to automate. SQL, on the other hand, works really well for when I don't understand the access pattern. So if I'm looking at an analytics workload, I have marketing people are coming in at the end of the week or the end of the month or the end of the quarter, and they have different questions to ask of the data, and to kind of help plan budget processing for the business or whatever. There's different things we need to know. If I don't understand the access pattern, I don't understand what queries might be asked of the data, or the nature of those queries is highly diverse and complex, then it might actually be a better idea to look at an SQL database that supports that ad hoc query processing. So that's really where it breaks down for NoSQL versus SQL. Do I understand the access pattern? Is it an OLTP app? Let's look at NoSQL. Do I not understand the access pattern? Is it an analytical or an OLAP type of application? Then maybe we should look at an SQL backend for that.
Mm-hmm. So when you talk about OLAP, just kind of to diverge for a second here, even SQL runs into problems with that sometimes, because
Sure.
You're trying to serve
Join big tables.
Yeah. So you make your query, and then 2.5 hours later, it's you get your
Right.
3-row response.
Exactly. Or it's a computed aggregation or some
Yeah.
sort of KPI you're trying to drive out of the system. And again, this is where NoSQL databases can really help you. And we'll do some similar things in SQL. As a matter of fact, in Amazon's retail organization, one of the reasons we started to look at NoSQL in the beginning was because we found ourselves denormalizing the data on the table. Right? Instead of selecting the count for the downloads of given song for Amazon Music, we would just go ahead every time someone downloaded the song, we'd bump a counter on a table. And so when someone came in to see how many downloads, they were just selecting the counter instead of selecting an actual count, which would have ground across the table and driven
Right.
the system to a standstill potentially.
Grabbing those opportunistic locks and saying, okay, hey, I've got to modify one thing, so let me just lock the whole row.
Right, exactly. And then you see as you lock multiple rows in a relational database, you can escalate to table level locks, which can create deadlocks, which we've all had to deal with in the past. I mean, these are really just not good situations to be in. So when you have these high volume kind of computed aggregations, oftentimes we can set those up in DynamoDB using a streams and Lambda process to do change data capture on the table and modify and update these top level metrics that on the in
Right.
other items, right?
It's almost like a cached aggregation.
It's like exactly.
It's like a view.
It's a view, exactly.
So we have a couple questions from the stream about table design, but before we go into that, maybe we can outline the different core components of DynamoDB.
DynamoDB,
So we could say what it is, what an index is, what a table is, what a row
Absolutely.
is, stuff like that.
So let's do that real quick. Let's talk a little bit about DynamoDB. What is it? It's a fully managed NoSQL database, and this by far is the most valuable aspect of the system. I've worked with customers that have the largest Cassandra clusters in the world, the largest MongoDB clusters in the world, and they're running into those problems of having to manage this infrastructure. It's not that the technology is broken. The technology is great. All NoSQL technology is relatively equivalent. It's and it will all scale, and every one of these platforms has their use cases and documented success stories, but the management is something that is kind of that is just pushed off onto the user. And it's one thing when I'm managing a single cluster, MongoDB replica set, 3 nodes, not a problem. Now add 10 shards, 15 shards, 20 shards, and the number goes up. And I've talked to customers with 500 nodes in their Cassandra cluster. They have 50, 60 full-time engineers running a 724 NOC, and all they're doing is rebuilding failed storage arrays and racking new hardware.
24/7.
24/7, right?
And ultimately, running the ops around the database is not what's providing your business value,
That's
right? It's actually
exactly
allowing
right.
your developers to leverage it in whatever your application is.
That's exactly right. So you're developing a huge amount of skill in an area that's not valuable to your business, right? It's kind of the same story we talked about back in the 70s and 80s without IT outsourcing. Do you want to be in the business of managing a data center, or do you want to be in the business of selling your product, right? So really offloading that management burden is the biggest value of DynamoDB. Other than that, it's a wide column document store. We can talk a little bit about the difference between wide column and document later when we get into data modeling. Suffice to say, I don't really say I don't consider them to be really all that different. It scales to any workload, fast and consistent at any scale, and I've never seen a NoSQL database scaled out to the level of DynamoDB. We have single tables running in excess of 7 million transactions per second. We did billions of transactions against DynamoDB tables on Prime Day just for Amazon CDO tables. It's an amazing system that has proven that NoSQL databases can scale to just about any workload out there. Fine-grained access control. We can control access to items on the table, to the table space itself, to attributes
through IAM.
Through IAM policies, and we can control access to individual attributes within the item. So I can
based
have
on conditions.
Conditions, exactly. So we can have some users that might be maybe HR or payroll accounting personnel that need to process commission data, and then we might have order entry clerks that we don't want them to see the salesperson's commission data, right? So we can see different views of the items on the table depending on the user.
And that's all done through IAM. So you write the IAM policy, and then boom.
Boom, and it just happens, exactly. And then again, it's a backplane service. It stands as serverless. There's no need to provision instances on EC2 to support DynamoDB, which means it's perfect for that event-driven programming or serverless programming model that we're trying to push people down, and which is a really powerful model. You can stand things up extremely cheap, and you don't even have to worry about paying for it until they show up. And that's, again, DynamoDB's elasticity and flexibility is unparalleled in the industry. There's no off-the-shelf NoSQL technology that allows you to scale as quickly and elastically and pay for what you use, right? That's a really big deal, right? When other NoSQL databases you provision for peak load, it sits there.
You basically charge every second that server lives, no matter how much of that database you're filling up.
Exactly, and it's a database, so you can never take that server down, because trying to stand it back up again means replication, means hours and hours, or even days and days. As a matter of fact, I wrote an article recently, it's up on LinkedIn, where I talk about the most miserable days of my NoSQL life, spending watching a MongoDB cluster, trying to add shard number 15, and saying, okay, every day in an ops meeting with my customer and saying, do we need to throttle our API more to free up more capacity on the cluster so this shard replicates in, and then
MongoOS.
And so that's a real problem with NoSQL databases at scale. DynamoDB solves that problem.
So we have a quick question that I think you can answer. A Russian bot, which is just the most ridiculous Twitch username, but a Russian bot wants to know what are the limits around DynamoDB?
So there are some soft limits in the account. When you sign up to AWS services, many of our services are going to have limits initially. The reason we do this is because if you want to exceed those limits, you just need to kind of pick up the phone and call support and say, well, not necessarily phone, but open up a ticket.
Yeah, I see a lot of those tickets are automated now. So you open it, and so long as you're It's almost to prevent you from shooting yourself in the foot.
That's exactly right, and that's really what it is, and also for shooting us in the foot, right? I mean, if you need 5 million IOPS on your DynamoDB table, I might need to rack some hardware, depending on what region you're going to, right? I mean, the cloud's great, it's elastic, but and it could scale to ultimate levels, but it's not infinite, right? And so there's just basically guardrails around what we're going to allow customers to do right out of the box. Most of the time, when a customer has a large workload like that, we're well aware of it before they even deploy. Right. But if you are scaling and having success, you don't have to worry about upward limit in DynamoDB. The biggest table, or the fastest table, I guess you'd say, that I'm aware of is about 7 million WCUs. So, and that is an incredible workload.
WCUs
is a write capacity unit.
Write capacity units.
Yeah. All right, so let's see what a table is, what a WCU is, what an RCU is.
Okay, so let's get into that. DynamoDB, like all databases, has tables. They're called different things in different NoSQL databases. DynamoDB calls them tables. MongoDB calls them collections. Cassandra calls them key spaces. Within these tables, collections, key spaces, whatever you want to call them, we're going to put items. These items have attributes. Not all the items in the table have to have the same attribute, but they have to have at least one attribute that uniquely identifies the item, and that's the partition key. In DynamoDB, we call it the partition key. Cassandra calls it a partition key as well. MongoDB calls this the underbar ID field, right? So this is that it uniquely identifies a document in MongoDB, an item in DynamoDB, so on and so forth. In DynamoDB and other wide column databases, we also allow you to create an alternate key called the sort key. So when we do this, what happens is the partition key starts to define like a folder or a bucket in which I'm going to place items, and the sort key then defines the uniqueness of the items within that partition, so to speak. So we're going to create hierarchies of items inside of these partitions that represent these one-to-many relationships, or these entity relationships that we would normally be creating individual tables for. You can think of these partitions as collecting the rows that build the entity that the application wants to consume. Right. So that's generally kind of the relationship we're going to try and draw here, excuse me. And then as we start to pull out subsets of these rows or whatever for different views that we would want on these entities, we're going to use range operators against those sort keys, right? Things like greater than, less than, between, whatnot, to be able to pull out subsets of items. So for a simple example here might be orders for a customer. I could say, partition key is the customer ID, sort key is the order date. If I want all the orders in the last 24 hours, select star from table where customer ID equals X, and the order date is greater than 24 hours ago.
And so, yeah, I was just going to say, so this manifests itself in the form of trying to understand the access pattern, right? So when we're trying to think about having some sort of time series data, date is the obvious thing you typically want to sort or query by. And so having that as the specific sort key will be really valuable in this use case. But depending on what your use case may be, time may not be the best sort key, right?
It could be, depending on the use case, right? If I have a time order use case, time would be a really good sort key. I might have a use case in which some are more, I want items of a certain type for a given customer. But then I might have other items that I want date ranged. So I might have some items in this partition that would live with a state identifier as the sort key, just to, whatever, it's completed, it's done, it's back ordered, whatever. I might have other items in that same partition that actually have a date as the sort key, right? They're both string sortable. One query condition gives me the completed items. I'm not going to get any date ranged items. One would give me a date range query, would give me just the date ranged items. So if I could even store items of different types, like we talked about in the table. Not all the items need to be the same type. Not all the items in a partition need to be the same type either. So we're going to be playing with these sort key conditions to produce the subsets of the items that we're looking for.
So let's talk a little bit about the query semantics here.
Okay.
If I want to query, let's say I want to fetch a specific item and I have a partition key and a sort key. Do I need to provide both of those in order to get that specific item?
That specific item, you would need to either execute a get item with the unique identifying partition and sort key values, or a query condition that would result in only one item coming back. Right.
And so are these different operators the ones like equals would result in one, and then less. So the combination of partition key and sort key are unique.
The combination of partition and sort key are unique. Yes, must be unique.
So that equals operator would be a query condition that would return just the one.
Well, depending on if you said sort key equals, then yes.
Yes.
But you can use these query conditions also as filter conditions on the extended attributes, not just the sort key. So I can make a read out of the partition and say, give me everything that has a sort key condition of X, and also filter condition of Y. in which case a filter condition of equal might return many.
Yeah.
Right.
Right. But if you put equal on a sort key condition, it's basically saying there can only be one.
And then I remember working on other NoSQL databases. I actually remember writing some code to implement parts of this. And different operators have different kind of performance characteristics. So is that true in DynamoDB
It is
as
true.
well?
It is true, and it also depends on the number of items that are coming back from the query. There's restrictions around how much data you can move in and out of a partition. We have plenty of content online to talk about that. If we need to scale beyond that, then we're just going to include more logical partitions in the workload. But yes, there's, depending on the nature of the query, the number of items that are being returned. In general, almost all of these range key operators in DynamoDB translate to a batch get item under the covers.
Gotcha.
Okay, so that's going to be, and a batch get item is going to be a little bit slower than a get item, and it's going to have a little bit more latency depending on how much is latency on the storage node there is.
And then we have attributes. These are things that aren't kind of captured by the partition or the sort key.
Correct.
And if we want to filter a query based on those, what is it essentially a table scan at that point?
Nope. At that point, then what we could do is we'd say, okay, if we know the partition in which these items live, then I could read the partition where the partition key equals X and then use filter conditions on the extended attributes. What I'm doing then is I'm reading the entire partition and I'm returning only the items that match the filter conditions.
But that's a job for the storage layer.
That's a job for storage layer. You as a user don't need to know this, but you do need to understand what you're doing when you issue those filter queries because again, I pay for the sort key condition read, right? So if my sort key condition is not very selective and my filter conditions are highly selective, then I'm going to be reading a lot of data and only returning a few items. And so this is a choice we might make in the design to actually query the partition inefficiently because maybe it's a infrequent access pattern. Right, so rather than set up a GSI that allows me to query more efficiently and double my write cost and double my storage cost, and I'll just say, you know what, I'll just read these partitions inefficiently every now and then when I need to because it's cheaper to do that than it is to maintain the effective or the selective index.
So maybe we can talk a little bit more about when you don't want to do that with
Sure.
global secondary indexes and local secondary indexes and stuff
Yeah,
like
when we
that.
get into that modeling discussion, we'll talk a little bit about that, absolutely. All right, so generally speaking, when we talk about NoSQL, we're talking about spreading that data out across what we call a key space, and we're going to use the partition key to do that. So the partition key uniquely identifies the item, but it also is used to build this unordered hash index, which is a logical key space, and we're going to lay these items out across that key space. And the reason we do this, and all NoSQL databases work the same way, is that when we want to scale, we're going to chop that key space up and we're going to distribute those items out around to multiple physical nodes. This gives me now the ability when I query the system to take that partition key value, which is an equality condition, and say, oh, you belong on node N. So I know exactly what node to go to, and it just logically you can think about this. There could be thousands of storage nodes participating in this key space, but as soon as you query the system, the request router knows exactly which system to go to. It doesn't have to query all 1,000 of them. So this is why NoSQL databases are fast and consistent at any scale, and it doesn't matter how much data is in the system, how much throughput is in the system. I can always allocate the data across physical devices on the key space and query with the same latency.
So request router knows exactly which underlying storage nodes it needs to talk to based
That's
on.
right. It has the map of the table space, so to speak. What sections live on what nodes. Now, it's not always clean where node 1 is responsible for this chunk and then the next chunk, and then it usually gets diced up and sliced up and pushed all over these storage nodes. But the system doesn't care as long as I give it an equality condition on that partition key. It knows exactly where to go.
And again, these are the optimizations that the user doesn't actually need to know, right?
Right.
Because this is done on the database's compute side.
That's correct. Absolutely. You don't need to know that. Although when you query the system, there's certain parameters that need to be maintained. So if you think of the partition key in DynamoDB, it's kind of like the shard key almost in MongoDB in this sense, right? Because that's what we're going to use.
In this sense,
yes.
yeah.
In the uniqueness sense, it's like it's almost like Mongo has two keys that do the same thing as
Right.
one key in Dynamo, right? But they're used for the same reason. So what determines where the data lands in a MongoDB cluster is the shard key. What determines where the data lands in DynamoDB or Cassandra is actually the partition key.
And it's just a different model, but you can build. One of the things that you taught me actually was that partition keys do not need to be a scalar value.
That's right.
You can combine multiple components, and if you know you're always going to have those two components in your query, then you can write your query in such a fashion that you combine those into a unique partition key.
Right, exactly.
And we actually have someone who just joined the stream, Matt Auerbach. So he was coding up a Twitch extension to build a multi-tenant polling system,
Okay.
a multi-tenant voting system. and he called me on the phone. I don't think he told me that he was streaming this live. or maybe he did, I don't remember. So he calls me up, he goes, "Hey Randall, help me figure out how to do this in DynamoDB." And then there's another viewer we have here, Richard Boyd, who, I was in the middle of something, I was doing some work, and it's like, "Okay, Matt, just do it like this, and I had to hop off, and then Richard Boyd hopped on the phone with him. So he was live streaming this whole thing on Twitch. And I remember I sent him maybe 4 lines of Python, and he said something to the effect of, like, "What do you mean this is all I have to do?"
Yeah.
He's like, "Oh, it's working."
Oh,
Wait,
what do you know?
He just totally didn't believe me, and I
Right.
think to this day he doesn't believe me.
That's funny. Oh man! All right, so then we get into looking at how the sort key plays here. Really, the sort key again, the partition key defines a folder or some sort of bucket. The sort key defines the order of those items on the bucket, and then when we go to read these items off of that partition, you're giving me that partition key equality. Says go here. Give me a range key. These things are all ordered on the storage node. It's just a sequential read to match the sort key conditions. That's what makes us fast and consistent at any scale. And all NoSQL databases share some sort of mechanism similar to this to provide that kind of performance, not just unique to Dynamo.
Ensure index.
Yeah, exactly.
So again, partition key generated automatically by the compute layer on the database, and then sort key defined by the user.
The partition key is actually defined by the user.
Oh, okay.
Yeah, there is no auto-generated, auto-incrementing keys in DynamoDB. As a matter of fact, that's a common mistake people make when they migrate their applications from a relational database to an NoSQL database is they assume there's value in those auto-generated IDs.
Monotonically
Right,
increasing.
yeah. And so what they'll do is they'll create partition keys, which are like a product ID.
Yeah, unique
Right.
ID.
But no one ever calls up and says, "Hey, you know what? I want to order product UUID or product 25." Right? They say, "I want to order, whatever the latest and greatest thing is from Sharper Image Catalog or whatever it is." Right?
And that really just launches right into that accesses pattern.
That's exactly
discussion.
right.
Yep.
That's exactly right. So what we want to do is select partition keys that are useful to the application, right? That they're gonna align well with your access patterns. Because think of that primary table as like that's your first index. Really, it's an inverted index and it's manually loaded. And that's one of the things that's kind of we got to start to think about with DynamoDB, with all NoSQL databases, because the indexes are how we're going to produce joins, right? So let's talk a little bit about those indexes.
Before we go into that,
Sure.
We have a question from Mittens the Killer Bunny, which again, great
Awesome name.
great usernames, everybody. Mittens the Killer Bunny wants to know, is there a downside to having locality, i.e. failovers, different nodes holding on to different partitions?
Okay, so a downside to having locality of the data on...
Yeah, so I think there's a misunderstanding there. Like the data isn't replicated to a single physical partition.
Oh, okay, right.
There's
That's right.
replication in the
Yes.
background
So
of the
in
storage node.
DynamoDB, well, there's multiple layers of replication now with global tables.
Yes.
But every storage node in DynamoDB is 3-way replicated across 3 AZs. When you write to DynamoDB, you're not going to get an acknowledgement that write committed until at least one of the secondaries has acknowledged that it replicated. So that makes us a durable database. Reads to DynamoDB by default will go to the secondaries. So those are eventually consistent. But you as a user have the ability to make that a strongly consistent read, which will force the read back to the primary. So this is like if you look at DynamoDB, MongoDB, these are consistent and partition tolerant systems, right?
Read concerns,
Yeah.
write concerns.
Exactly, and so we can do both the same things, right? Cassandra is an available and partition tolerant system because any node can accept the write. That's what they call master, and there'll be some sort of conflict resolution if I write to the same item in 2 different nodes and they get back together. There'll be some sort of callback to a conflict resolution algorithm. DynamoDB provides this type of functionality as well, but globally. So when you have a global table in DynamoDB, what you're doing is you're replicating your data across regions, and those regions can act as master, and they'll all accept writes. And then we have a conflict resolution, which is time-based. So we clock sync across the regions. If I write to a global table in region A and region B at the same time, eventually it'll replicate and we'll drop the older data.
Interesting. Does that save time in terms of the requests? Like, if you can hit whatever the master is that's closest to you?
Yeah, it depends on the nature of the application. We have a lot of customers, that was exactly what they were doing. A customer would hop on a plane in the EU, he would land in New York, and we wanted to work with data locally. So all they were doing when he's in the EU, his data's replicating over to New York, he flies over to New York, and now his locality determines hit the local instance. Yeah,
Awesome.
Yeah.
And the kind of follow-on to that is, let's say we're not using global tables. I think global tables, global multi-master is kind of a crazy thing. I think it's crazy that it exists. I use it in a couple of different machines I have, and the ridiculous thing was it took me 3 lines of code to enable, and it was one command line call, and I was like, hey, AWS, get available regions for DynamoDB. Okay, create new global table, and
add these regions. Boom. Yeah.
It's just working.
Wow. Yeah.
And then I could have the Lambda at edge functions going and talking and saying go do this. But let's go back to that single regional table. You talked about consistent reads or eventually consistent reads, and I'm curious, what is the kind of when you talk about read replication or something like that in a lot of NoSQL databases, people are talking between single-digit milliseconds and 100-digit milliseconds.
Sure.
So what does that look like in DynamoDB?
Yeah, that's a good question. We get that a lot. So the P99 latency on secondary replication in DynamoDB is sub 1 millisecond. So it's fast. P99 latency on when we get into talking about indexes, there's 2 types of indexes in DynamoDB, but the index replication for GSIs for global secondary indexes is sub 10 milliseconds P99 latency. So very, very fast, even for secondary indexes.
But when you create those secondary indexes, do they have to be kind of write and read scaled to the same? Okay.
Well, so again, different things. So we're getting into index.
Sorry.
So no problem. So let's talk about a little bit about indexes. There's 2 types of indexes in DynamoDB. We have what we call a local secondary index and a global secondary index. We'll talk about locals first. Locals allow us to resort the data. So if you look at the example we had earlier, customer ID and order date, right, as the sort key. So customer ID is the partition key, order date is the sort key. I might have a secondary access pattern that says, I need to get all the back ordered orders for this customer. So I might then create an LSI, which is partitioned on the customer ID, which is the same partition key as the table. That's required for LSIs because, again, I can't regroup the data. I can only resort the data. But I'll use an alternate sort key, and that sort key could be order state. And now for the primary workflow of customers' orders last 24 hours, I'll go to the table. For customers' orders by order state or back-ordered state, I would go to the LSI. LSIs allow me to resort the data. All indexes in DynamoDB allow me to project additional attributes onto the indexes. So this is a key difference between like a DynamoDB and a MongoDB. Right? When I query MongoDB and it's the same kind of semantic, it's going to go it's either going to find the item right off the collection because I gave it an underbar ID as a condition. It's going to say, great, I know where that item is. Or it's going to say, I don't know, do I have an index that matches this query? But when it queries the index, it might have to go back to the table to read those items to populate missing data, right? If the query wants attributes that are not on the index, it has to go read the documents. So in DynamoDB, to avoid that secondary read, we allow users to project some or all of the attributes from the items on the table into the index. So it's not just it's not just a B tree lookup, right? It's a storage mechanism. It's an alternative table, right? So now it makes the lookups much more efficient. So if I query a MongoDB collection and I want to match these items, it goes to the index, it looks at this nice efficient query, and it comes back and it says, you'll see if you analyze the query, it'll tell you, documents scanned, right? Documents returned and documents scanned, something like that, right? That's what it does, right? When you do an explain.
So and a couple other things.
It'll
tell you, kind of.
Right, but so if I query for only the attributes that live on the index, then it's going to say documents scanned 0, documents returned whatever 100.
Right. Yeah.
But you'll never see that in MongoDB because workflows are always going to require parts of the items, and those indexes are just there to look up. So what you usually see is documents scanned 100, documents returned 100. If you see a larger document scan, the documents returned, it means you didn't have an index and it did a table scan.
So essentially, by being able to have these attributes listed as LSIs, the user can still query in a very intuitive way, but the compute layer on the database will actually essentially rearrange the query structure under the hood to make it more efficient.
Well, when you create the LSI, we will rearrange the data to make it to match the pattern that you specify in your LSI schema. When you query the LSI, what's going to happen is you're going to match whatever based on the partition and sort key attributes that you specify, and then if you need extended attributes and you projected those on the index, then when the application gets the result set, it's not going to have to go back to the table and say, batch get item, all of these things to get me the rest of the data. Right? That's the key.
I use DynamoDB quite a bit, and I never really realized that you can project other attributes into LSIs.
It's important.
That adds so much value to
Absolutely.
The LSI. I can't believe I missed that.
Yeah, no, it's okay. A lot of people do. And so you can choose keys only, which is basically, hey, give me all the items that match. I don't care about the data. I just care about the match.
Right.
Give me some of the attributes because these are the only attributes I need, and we'll do this to vertically partition those items. I might have real big attributes in this item. item, and on the index lookup, I don't care about that big data. Think like a dashboard view for your email, right? When I look at my inbox, I'm not looking at all the bodies. I only look at the body when I select the item. So different ways to set up the workflow to be able to match your application's workload requirements. Very cool. So global secondary index is the other type of index we have. These indexes allow us to regroup the data. So in the example of, again, we'll stick with customers and orders. When a customer makes an order, his sales rep sold it, and maybe I need to get sales reps orders for the last 24 days to rank my salespeople on performance. So one workflow hits the table, gives me a quarter customer's orders in the last 30 days or whatever. The other, now I create a GSI that's partitioned on the sales rep ID and sorted on the order date. And what I've done is I've regrouped the data. Right, so now I have a totally different aggregation of the data, and this is really if you think of this, if I start to index across different types of items, then I'm really using my indexes to join this data, and this is what all NoSQL databases do to produce those joins, so to speak. Is you're just going to decorate the items that you want to show up with the same index attributes, and then use a specific query on that index to produce the aggregation that you're looking for, or the join data set you're looking for.
Do you think GSIs are a different, are they different from views?
They are views.
They are views.
They are views, right? Yeah, absolutely. That's the way I kind of define a GSI.
So if you're trying to
LSI.
Teach what a GSI is to a person with a lot of relational database experience,
I talk about views.
You talk about
yeah.
views. Okay.
yeah, absolutely. All right, so we can talk a little bit about data modeling, and this is where we get into actually looking at how do we map the data. And one of the things we found at Amazon is that it's funny, but all the data is relational. Yeah.
So there's no real such thing as like non-relational.
No, there's no such thing. It's actually a misnomer. I found this out quick. That's actually a marketing term. It was built by salespeople who didn't understand. Well, if it's not relational, it must be non-relational. They need to be able to explain it. It's actually denormalized. It's a denormalized data store, right? Yes. And so there is really no such thing as a non-relational data because all the data is relational, or we wouldn't care about it, right? I mean, there is a key value lookup pattern. There's no doubt. There's a very valid pattern. User session data, all kinds of examples of where where non-relational data plays, but the reality of it is that data is relational. Doesn't matter the app you're building, social networking, document management, IT monitoring, it doesn't matter. It's all relational. And the way we've done it in the past is using these normalized data models.
And I feel like this was a great way for people to waste time.
Exactly.
You were adding value. You were a database administrator. And I don't mean to take away from anybody's role, but I've worked with a lot of folks like this in pretty large businesses who their sole job was, let me make this into normal form. Let me add, 6 different double foreign key tables to create this relation. And,
that's right. Or figure out how to index to be able to accelerate my query performance, or whatever, right? What we're trying to do is
Well, so I was going to say, we had that slide before about like where on the curve are we
Right.
for NoSQL technology, and like, do you really think it's like an awareness issue? Where do you think that disconnect really falls with people realizing?
It's that the chart, the hype curve chart, is where it falls. People we're way up on that hype curve right now, where everyone's saying this is the answer, this is the answer. They're all running to it, and they're trying to do the same things the same way as the old technology. And funny thing, NoSQL is most effective and most efficient at scale.
Right.
I mean, relational databases worked fine for 30 years doing all kinds of workloads. There's nothing
With
wrong
no
with
real scale.
Yes, exactly. And 90% of applications today don't scale to the point where they actually need NoSQL.
Yeah.
So you can do it really badly and not really know it.
Yeah.
And so this is what's happening right now. I think this is what's delaying that evolution of on the adoption curve, right? Is that people are actually getting away with doing it wrong.
And that's like what we talked about before when I said it's kind of a difficult problem to assess because it's not just about, hey, do I check these boxes?
Right.
It's about, well, I have to figure out on my own whether my access patterns are properly aligned for this solution.
That's
and
right.
That's a hard problem to
Oh,
solve.
that's exactly
it's
it. That
huge knowledge
is
problem.
the opposite of relational, right? In relational database technology, we're going to normalize the model, and then we're going to start writing queries.
And
right?
you know that if you can just jam it into the normalized model, that it'll work.
We'll make it work somehow. Right?
Exactly.
Whether I need to add a couple indexes here and there, create some more efficiency.
Create the most ridiculously complicated ORM in existence.
Sure, exactly, but it will work, right? Whereas with NoSQL, it's the absolute opposite. We have to understand every access pattern. We have to understand the velocity of the workflows. We have to understand the nature of the data, the size of the data, the life cycle of the data. We need to know everything about the workflow in order to be able to optimize it. Why? Because we're denormalizing the model. We're tuning this specifically to an access pattern. And if we're wrong,
it's purpose built.
It's purpose built. It's a definition of purpose built, right? But the thing about it is, it's not terrible. We go through this all the time. I've been through this with 1,000 teams. It's a very simple process. Identify your access pattern. Let's define your entity relationship model. Guess what? You don't get away with not doing that. We still have to do that. The application cares about it. And then figure out how to map the model into a denormalized structure to satisfy your access patterns, right? And so it's a pretty straightforward process. It's just different than what we're used to. So this is our relational database right here. We've got product catalog, one-to-one relationships between products and albums, products and books, products and videos, one-to-many between albums and tracks, many-to-many between videos and tracks, and that's the list of queries we'd have to run to get a list of my products, right? No SQL database. Let's take that hierarchy of tables, collapse those rows into a hierarchy of items. Maybe a hierarchy of items that live in a single partition, or in this example, items that actually contain all of that data. These would just basically be product blobs, so to speak. And now select star from products brings back everything. Much simpler query. And this is what we're trying to do with NoSQL databases. We want to reduce the query complexity to eliminate joins. Everything should be select star from where x equals. Right. As long as we can just say star from where x equals, that's a simple query. Even relational databases blaze at those types of queries. It's when we start to join the data that the CPU goes crazy. Right. So let's avoid those joins. So we get into modeling for DynamoDB. It's really about two things: selecting that partition key and selecting the sort key. Good examples for partition keys would be, maybe a customer ID or device ID. Again, we want things to start to map to access patterns, so this might not be very good choices. If I had no access pattern, which was select by customer ID, then I wouldn't want to use that as a sort key, but many would. The bad examples would be things like status, gender, right? Binary, true, false. Oh boy, that's terrible, because now all of a sudden I'm limiting the number of storage nodes that can participate in the query workload, right? If there's only 2 partition keys, then there's only 2 potential storage nodes. So the size and scale of your data is going to be a real problem. Sort keys, it's about that modeling those relationships, the one-to-many, many-to-many relationships in your application. We want to try to design efficient selective query patterns. Again, we don't want complex queries. I don't want to have to make multiple round trips. One of the best ways to know that you're blowing it with NoSQL is if I'm getting something like select my customer metadata, so I can get my customer ID, so I can go to my orders table and select all the orders that match that customer ID, and then I can iterate through those orders and go get, for each one of those, get the items that belong to that order. Okay, that's a relational pattern. We're making a mistake here. Let's create a partition for this customer that's partitioned on customer ID, and then maybe a composite key for the sort key, which might be order ID dash item ID, right? Something like that.
Now that's something I notice a lot of people don't get, is those composite keys. They don't think about things like that, and it's because you would never ever do that in SQL.
That's like
And so I think that's something to really kind of drive home for people is what are the real world examples where you do that sort of stuff.
And we'll get into that when we start talking about some of these examples. So if you look at data modeling and the process of data modeling, this is what we talked about, the difference between relational and denormalized data modeling. It's about understanding that use case. We need to know what's the nature of this application. Is it an OLTP application? Is it an OLAP? Is this a decision support system? That OLAP probably doesn't fit. Right? I could throw it out right there and say that's probably not a good application for your NoSQL database. Now, the decision support system, I'd argue, might be, depending on the nature of the queries, the type of latency that you're looking for, and the performance you're looking for, and the scale. But that OLTP workload, that's our sweet spot, right? That's where we want to be. We want to define that entity relationship model. We want to define that data lifecycle. What are the TTL requirements, backup, archival, etc. And then the biggest, most important part of all of this is identifying your access patterns. So there's going to be some set of access patterns when we start building the application. You can almost pull them out of your user stories. Right? If it's an existing application, I can just look at your existing SQL.
Do you find that people go and work from their front end, the queries that the amount of data they need in a single round trip between a user input and what they're going to render on the screen? Do people ever go and say, okay, this is how I'm going to design my schema. This is my access pattern. This is what the user's asking for?
I find that most people end up breaking it down into a normalized model, even in NoSQL. The people who know what they're doing do exactly what you just said, right? They're saying, okay, what is the nature of the data I need to bring back to satisfy this access pattern? And generally speaking, if it's some sort of a user interaction, UI paging or whatnot, I want that query to be a single query that returns all of the results that I need to populate that dashboard view. Right. I don't want to have to go and query the database 10 times. or query 10 different tables. I want to make one query to get that data. And we're going to do that because we're going to use indexes to aggregate the items and composite keys and all kinds of neat tricks that we're going to use to be able to stow these items in partitions that are going to be able to be retrieved in a single query. And that's the power of NoSQL.
And ultimately, the querying and filtering is always going to be more optimal done on the database than any code you're going to write yourself. So it's not even a matter of like, hey, you don't want to write this code. It's always just going to be more performant.
It's just going to be better, right?
Yeah.
I mean, think about that, right? If I have to go through iterating from orders to order items for each customer, and maybe I've got a workload that says, give me all the orders in the last 24 hours for these 10 customers. Yikes, that's going to be a lot of queries, right? So, versus, hey, 10 customers, I might say, okay, let's make 10 queries. Okay, I'm okay with that, but I don't want to make, 1,000 queries to get
to render one thing for one customer, and then you have to throw it over to Redis or Elasticache or something.
Right, exactly.
So we've only got maybe 10 minutes left. So let's try and bowl through this, and then we're going to take all of the customer questions that have been collected.
Okay, let me go ahead and pop forward into some of the data modeling sections, but go ahead and fire up a couple of questions.
Yeah, so one of the questions that Richard Boyd and a few others asked was, and I can't remember the other person, but it was Gira64 or something, asked, it seems like you can do everything in a single table. Do you see people doing stuff with multiple tables?
There's reasons for it. They're rare. Yeah, I mean, most of the applications I build, it's basically one application, one table. I would say one application service, one table. So if I have, I definitely draw a boundary around services, right? I mean, inside of Amazon, we have 354 tier 1 services. Those are our money makers. When one of those is down, we're losing money. Every one of those is comprised of multiple microservices. And inside of each one of those, I would draw a boundary around the table. So almost tie the API to the table, I guess. Multiple tables might exist inside of a single service if I had maybe a configuration data that lived on one table and it was never accessed on the same pattern as the actual instance data. I might store instance data on one table and configuration data on the other. If the access patterns are completely isolated, the data is completely separated, then it really, having it on one table is not a real advantage, other than operationally less things, right? I always like less things, right? No, seriously, less complexity, less tables, less alerts, less alarms, less capacity allocation.
Less things for the brain database
Less
to keep in mind.
for the brain database to worry about, right? So that's why I like single table designs, but in certain situations, I'm not opposed to multiple tables, but I would like to see those access patterns completely separated. The nature of the data should be completely separated. There shouldn't be any relationship between the two.
And we have another question from David Wells Codes, which is what's the developer experience like when you choose the wrong access patterns or you misidentify those access patterns?
Really good question. I get this a lot. So typically what's happening is we're aligning those access patterns to the user stories that you're building your application around. So if you pick the wrong access pattern, what you're telling me is you picked the wrong user story, which probably means you picked the wrong app. But that's okay.
So your entire business is destroyed.
Your entire business is kind of, but that happens a lot. No, so really the biggest issue with NoSQL is when I need to add new access patterns. And this is, it's not typically that we pick the wrong access pattern. That does not happen very often. But I have lots of teams come back to me and say, hey, Rick, we did this and this and it works great, but customers come back and say now they want X. How do we do X, right? Yeah. So X can be added into the system by, typically it means decorating the existing items with additional metadata, maybe running a table scan and writing back to those items some attributes that didn't exist originally that you want to exist now, because I'm going to be filtering on those, I might be indexing on those, or I might add new partitions, new types of partitions with relationships to other partitions. Again, it's
new GSIs.
Right, new GSIs. Again, it's really more of an enhancement to the model. This is what I've seen 99% of the time. It's an expansion or an extension of the existing model. It's not a reworking of the model. If we're in a situation where we are reworking the model, it's probably because we did something wrong when we were identifying the access patterns. Typically, it's not a modeling issue. It's more has to do with velocity of the access patterns. That's where people miss it most often. I didn't think it was going to get hit that hard, right? And so then we're going to have to do things like start to spread the data out and whatnot. And again, these are really just kind of tweaks on the model, not like redesigning the model.
Okay, folks. So we only have a couple minutes left. Please get all your questions into the channel. I will relay those to Rick, and even the ones we can't answer on the stream, we'll try and answer asynchronously. But Rick, let's go ahead and see a couple of these examples here.
Sure. You know what? And what I'm going to do is just going to roll forward to an actual model that we built for one of our internal service customers rather than, here we go. So I don't know how many folks on the phone right now have Kindles, but if you have a Kindle, There we go. It should be up on the screen now. If you have a Kindle, then you have access to the Audible ebook versions of your ebooks. And if you're a Prime user, then you actually have access to those Audible ebooks for free. So go sign up for that service. This is the service that actually syncs between the Audible ebooks and various points in your various devices within the customer's family of objects that they're listening to these ebooks on, right? So if I drive into my driveway listening to an ebook on my Alexa in my car, and I walk in and I start to play that in my house, it needs to know where to start. Okay, so this is I wouldn't say simple, but it's relatively straightforward. There's this big mapping table in the middle here that maps all these many-to-many relationships between the products, which are ebooks, and the audio products, which are A-books. And so an ebook can have many audio products, an audio product can belong to many ebooks, because an ebook can belong to multiple volume series, editions, and whatnot. Mm-hmm. And then there's many types of devices that these audio products can play on. So there's many different audio products that actually correlate to the ebook, because I might be playing on my Alexa, I might be playing on my Kindle, I might be playing on my laptop, so on and so forth. And then there's this little ACR info table that sits off to the right, and that's the sync file record. Right, saying here's where I stop.
How far along?
Right, how far along? Right.
Yeah.
And again, many mappings between all of these things, between products and audio products, between ACR info and audio products, and so on and so forth. And this team was having a real difficult time trying to map all their access patterns into a denormalized data structure, because they had a lot of them. And so.
Well, you just right?
Yeah, just shove it all together, right?
and then you're back to SQL, right? We're back on one table.
No problem. So anyways, what we did with these guys, sat them down and said, okay, what are all your access patterns? They had an existing application. They went through all of the various SQL statements they were executing against the system. They came up with 20 different access patterns against the data they needed to support. Variety of dimensions, variety of filters and conditions, a lot of upstream and downstream consumers. And so again, they're having a lot of trouble trying to map all this data into a single data structure. So we took those patterns and we created a base table that looked something like this. Now, this is a fairly complex design. If you want to understand the ins and outs of this, I suggest you watch the DAT 401 session from reInvent, where we kind of break down a lot of the design patterns, right, that we're showing here. I'm going to describe this thing at a high level. You can see we have two different types of partitions on this table. We have an A-book partition, we have an E-book partition. The A-book partitions are tied to the E-book partitions using these items that live inside of those partitions that have an E-book ACR as the sort key value.
And that's a composite.
That's it. That right now is not a composite. That's just a simple E-book ACR ID. So,
sorry, I was looking at the A-book one.
Yeah, A-book one above it starts to become now. The A-book one is interesting because it's versioned. Right?
I see. That's the
that's the V0, right? So V0 is the current version, right? So as they add new versions and they add V1, V2, V3, they're going to clobber V0 with a copy of the new version, and they're going to maintain the whole version history in this partition. I'm not showing that version history here, right? So they can come in, they can say, hey, get me A-book ACR 1, starts with V0. It gives them the current metadata for that A-book ACR. They could say greater than V0. It gives them all of the history of that A-book ACR.
So then the application essentially becomes responsible for constructing that query.
That's exactly right. So it's query conditions that return the actual items that you're looking for. So if you look at these individual items on this table, again, we tied the A-book ACR partitions to the E-book ACR using that edge item. I mean, this is really a classic graph, right? It's an adjacency list, right?
Yeah.
Think of these partitions as nodes. Think of these edges like that E-book ACR edge as or that item is the E-book ACR item is the edge that connects the two. So if I put a GSI up on the sort key, you'll see all the edges that are connected to me, right? All the
Totally different.
It's one side or the other of that many-to-many relationship, right? This is what we're trying to do. We also built a one-to-many relationship inside of those A-book ACR partitions using these track items, right? So we have A-book ACR has multiple tracks. So it's tied to the E-book ACR. It's tied. Here's all the tracks that are associated. Here's the metadata for the A-book. Version history on that item, which is what the team needed. Anyone changed anything they wanted. And then we went and created E-book ACR partitions with just a single item. And then what we're doing is decorating all of these items on these GSIs with the various attributes that they're being looked up. So if you look at this access pattern, get this by that, get this by that. What we're doing is solving every single one using these GSIs. And when you look at the data on the GSIs, it's like, oh, wow, that's ugly. right? I mean, you wouldn't want to have to kind of sort through this as a human being, but it's a good thing that we're not. And, I get this a lot from teams. Well, if I need to visualize my data, it's so bad. I'm like, okay, I don't know how often you visualize a petabyte of data, but I don't, right? So, so honestly, what we need to do is get over this fact that there's different data on the table, because that's the way NoSQL works. This is how it's going to work efficiently. And then, so you can see the data is distributed across all those GSIs, various dimensions, various types of data, and then we're going to take that, and this looks like an eye chart, and it is, but we're just taking those 20 access patterns, we're adding those 3 columns on the end. Query this table or this GSI, query it with these sort key conditions, and query with these filter conditions, and this is going to satisfy your access pattern. So it's a pretty straightforward process.
It is straightforward, but it's also an ingenious design. Did you come up with this?
Yeah, this one was
okay. Yeah. I mean, this is deceptively simple. I mean, sorry, it's incredibly simple, but
deceptively complex. Yeah,
it's the same thing where you look at the answer and you're like, oh, I understand this. And then it's like, okay, now do it again. Now solve it, and that's the whole issue.
That's right. Yeah.
Yeah. This is absolutely brilliant. I'm ready to quit the stream because I have to go write a lot of notes and I want to go change. I want to go change a bunch of things around. I mean, I've learned a lot today. So
awesome.
Let's see if we can't answer the last few questions from the stream here.
No problem.
So I think we had a question from Trond Hines. Given a traditional relational database with a customer table and an orders table, what would be the best way to think about situations where the customer address gets an update? A relational DB would handle that easily since it's one-to-many relation. But how would you design a relation like that and the flattened structure of a document DB? And I know the answer to this, but you can.
Okay, you can test me. This was customers and orders. So really what you're going to have is customer metadata and you have order metadata. So I would start to look at what is the access pattern here. Maybe let's assume that it's a dashboard view. Customer logs into their portal. They want to see the last month's worth of orders. So that'll be actually my query. You'll say, give me everything in this customer partition that has a sort key attribute that is greater than 20 or 30 days ago. The first item I would load in that partition would be the customer's metadata item. That would have his address, name, login data, all that stuff. It's a single item, and it would have a sort key value of 9999.
And I think one of the things that people don't always get is when you say partition, it's really partitions, because it's a type of partition, but it's a It's multiple partitions.
Yes, it's a customer's partition. There can be many partitions that belong to many customers, right? So every customer has their own partition that's identified by their customer ID. Inside of this partition lives a customer metadata item with a sort key attribute of 9999 or just 9. And then all the other items in there are order items, and they have a date as the sort key. And then I'd say, give me everything that's greater than 24 or than 30 days ago. Well, guess what? 9999 is greater as a string sort than 30 days ago. So I'm going to get the first item that comes back is going to be the customer's metadata, and everything after that's going to be an order. So inside of the application's logic, when the result set comes back, it'll process that first item as customer metadata, populate address, login name, all this kind of stuff on the dashboard. And then it's going to say every item after that goes into the table and describes the actual orders that the customer made.
And you and I, we had a conversation actually about something similar to this on Twitter, where you did the for each.
Yeah, exactly. That was the MongoDB, how you update, right? So
you could just update everything.
Yeah, just update everything. Well, in this example, what I just put out was a little different because we're not actually updating any of the order items because they don't contain the customer's order address or address data. Only the metadata item does. But I'm creating a query construct or a data model that allows me to query it with a single query and get the customer's metadata and all the orders. The same way I would as if I issued a join in a relational database.
Right. We probably have time for maybe 2 or 3 more questions.
Yeah, I have one from the chat here from Thomas Whiston. So a nice foil to the last question we had. For admin interfaces where a few users need to query data using search or filter fields, it may not make sense to define all search fields as access patterns. Would it make sense in situations like this to scan the table?
Sure. So 2 things can happen here. I have lots of situations like this where we need to do searching on multiple dimensions. Don't forget about filter conditions. Right? Filter conditions can be your friend here. As long as the sort key condition is relatively selective and the filter conditions are just kind of trimming the items out, or even if the sort key condition returns a lot of items, but it's not a high volume, right? I mean, if we're talking about gigabytes of data and filtering down to a few items, then that's a problem.
Yeah.
But if what we're talking about is, hey, I'm bringing back a megabyte of data and I'm going to be trimming out, a couple hundred kilobytes, then that's not too much of an issue. So filter conditions can work very well. The other thing that can happen here, again, depending on the nature of the access pattern, you might want to create a selective index that's specific for the dimensions that you're querying on that'll allow you to kind of create that selective first step and then filter on the rest. But typically, this is where I start to wonder, is this a good pattern for a NoSQL database, right? Because now if you're talking about querying on a large number of dimensions in a random combination, what you're really talking about is ad hoc queries. So let's really look at this and determine whether or not this is a good use case, for a relational database. And maybe the other option here is potentially bring in Elasticsearch.
Okay.
Because we can query against multiple dimensions, Elasticsearch, and identify the items we need on the table. That could be a really valid architecture as well.
Awesome.
So, I mean, Rick, we're gonna have to have you back because there are so many things. There are so many things we never even got to. Things like DynamoDB streams, things
I know,
DAX, and
absolutely, I'd love to come back. Absolutely.
Yeah. So we're gonna Nick and I are gonna work on the schedule, get you back here, maybe sooner than
later.
Than later.
There you go. All right, sounds good.
I just wanted to say everyone in the stream has been very kind to you and saying that you're a wizard and that they learn something every time.
Awesome. I appreciate that. That's what I live for. So thanks for that. That's really cool.
So thank you so much for coming on, and we'll be back next week with another episode.
Yeah, next Tuesday at noon here at twitch.tv/AWS. Thanks for tuning in. We'll see you next week, everyone.
Bye,
Thanks,
everybody.
guys. Bye.